Hi, I'm Flavio Cavalieri. In this video, we're gonna talk about queues. Queues are a very important and useful mechanism in real-time operating system. With a finite number of fixed-size data items, they offer communication between tasks and interrupt service routines. The communication direction can be from task to task, task to ISR, and ISR to task. The next picture shows us two concurrent tasks working together, a receive data task and a send data task. The receiver task is a high priority task. Look at that. At this moment, it attempts to read data from the queue, but the queue is empty. So, the receiver enters in block state. And now the sender task enters in run state and adds data to the queue. The high priority receive task preempts the sender task and starts to receive the queue data. The receiver tasks enters in block state again. So this is basically what you see here in this graphical representation of two concurrent tasks working with the concept of queues. So let's understand the queue manipulation process with the following example. So the queue is created with a finite number of fixed size data items. In the example here, we have 5 integer size values. Just an example. So task send adds the first value in the queue. So you can see here the value 5. Task receive remains in blocked state, and task send adds a second value in the queue, value 6 here. Now the task receive enters in run state and attempts to receive the queue data. So the first value in the queue, the integer value 5, is received by the task and will be removed. The second value will be moved to the one in the front of the queue. There are two possibilities for queue behavior when it's implemented. The first one, it's queued by copy. In this case, the data is copied byte for byte into the queue. The second one is the queue by reference. In this case, the queue holds pointers instead of data itself. Be careful. When working with queues, passing values by pointers, it's important to use semaphores in order to avoid any change in the memory content till the receive task finish the reading. So before starting our examples, let's dig inside the queue documentation. So here in FreeRTOS.org, under the API reference, we can find information about the different objects in the FreeRTOS API. So here, under the queues, we have a bunch of information here regarding queue functionalities. So the first function we're gonna explore here in the FreeRTOS API related to queues is the queue create. So basically the queue create function creates a new queue and returns a handle, okay? And this handle, it's used for many things like reading, seeking, writing, deleting operation, okay? It's very important. And also check here. For example, if the xqueue create returns a null pointer, this means there is not enough memory space in the heap, for example. So if you don't have enough space, okay, to create here your queue in the heap memory, it will return null pointer here. Okay, this is one case that returns null pointer when you call xqueue create. So you need to pass two parameters here for the xQCreate function. The first one is the queue length. Okay, how many items your queue should hold in this case, the queue length. The second one is the item size. So each size, each single item, okay, each single item here, how many bytes, the size for each single item in your queue. Okay, so this is basically the first function we need to understand about the queues. So moving forward here in the documentation, we can see a usage example for queues. So this example will create basically two different queues. The first queue, as we can see here, it's based on an unsigned long variable. So unsigned long variable is a 4 byte variable. So in this case, we're gonna create here in this example, okay, 10 different items. Okay, so 10 different items in our queue with one signed long value for each item. So 10 times 4 bytes, it's equals to 40 bytes. So it's very important to understand. Those 40 bytes will count in the config total heap size. So the config total heap size, just to remember, it's basically the sum of the different memory allocations in our FreeRTOS objects. Like, for example, a semaphore. When you create a semaphore, this counts in the config total heap size. When we create an item list, like we are doing right now, this is also memory space allocated from the total heap size. The stack of the task 1, stack for task 2, and so on. So those simple things here will consume the memory configured, the heap memory configured by the total heap size. It's very important to understand that. So here we have a 40 bytes, the total size for our item list, but the queue itself also consumes some memory. Okay, it's called queue control block. So the queue when you create it, they also consume some memory in the heap. Okay, the second one here, the second queue, it's also a 10 item queue, but the data size for each item here is different. So it's the size of the struct A message. The struct A message, it's basically a char message ID and an array with 20 different data here with char size. So we have here 21 bytes in total. 21 bytes times 10, it's equals to 210 bytes. So the second queue here, the item list, it's 210 bytes. The first queue, the item list, is basically 40 bytes. All right, another function gonna work in our examples, it's the queue send. Okay, this is a macro, the queue send, that calls xqueue generic send. Okay, this is included for backward compatibility with versions of FreeRTOS that did not include the xqueue send to front and xqueue send to back macros. Okay, this is equivalent to xqueue send to back, the xqueue send function here. It's also important to mention here there is a specific function for ISR, interrupt service routine. So when we want to send the queue information directly from an interrupt service routine, you need to call xqueue send from ISR. Okay, so this is very important to know. So let's tell important information about XQ send to back, which is basically implemented here when we call XQ send. So this is the XQ send to back, okay? And basically here, what is going on when you call XQ send, and it's XQ send implements the same thing of XQ send to back. This sends data to the tail, to the back, to the tail of the queue. So when this send data, it's important to know that this will put the data in the direction of the tail, okay, in the back of the queue. So it's the direction we're gonna use to save data in our examples here.
And the other one, send to front, as the name says, this sends data to the head, to the front of the queue. Okay, so you're gonna use the XQ send, which basically implements its equivalent to the XQ send to back. So it's equivalent to XQ send to back. All right. So let's explore the Q send back function. So as you can see here, this function needs 3 different parameters. Okay, the first parameter is the handle, okay, on which the item is to be posted, okay, as explained here. The second one, okay, it's a pointer to the item to be placed on the queue. And the third one, it's the amount of time the task should block, waiting for the space to become available on the queue. Okay, that's it. So if the queue is full, okay, this function will basically wait for a maximum time, for a maximum ticks, okay, and this call will return immediately if this is set to 0. So if this parameter is set to 0, this function will return immediately, even if the queue is full, okay. So it's very important to understand the behavior of these functionalities here when you pass, for example, a 0 or infinite time or some delay here as well. So you're gonna understand these possibilities in our next examples and the behavior at the end. Next function we're gonna explore is the XQ receive. Okay, this macro calls the XQ generic receive function. Okay, basically, and this will read data item from the queue. So basically, the queue receive will read the data item from the queue. Okay, and very important, soon as read the data, the queue receive, this will remove that data from the queue. It's very important. Queue receive, read the data from the queue, and remove this data after reading. Okay. Okay, the first thing here, the base type T here, the return of the queue. Okay, this returns true when it reads with successful, when successful reads. Okay, but this can also return queue empty if the queue is empty after waiting for X tick to wait, the third input parameter here. So we have three parameters, okay, the queue handle as we already explained it, the buffer itself, this is the pointer which will hold the data item received by the queue, and the third and very important, the maximum amount time the task should block wait for an item to be received. Okay, so this can be also set to different possibilities, and we're gonna explore, as I already mentioned, those different possibilities in our next examples. Last but not least from this explanation, the XQ peak. The difference from the previous one, the Q receive, is that the XQ peak, in this case XQ peak, this will not remove the item.
from the queue. This will read the data, will take the data from the queue, but will not remove the data. This is the main difference between queue pick and queue receive. So our first examples will be based on a counter, okay? And this counter will increment the value. And each incrementation here will add this value to a queue in some specific task. Another task will do the reception, the buffer reception, the queue reception. And we'll save this value in one variable, and this variable will be monitored by the serial. And afterwards, we're gonna explore also and understand those behaviors using the Sega system view. But very important, before enabling the USART peripheral under the configuration tool, let's make a backup from FreeRTOS config.h file. Otherwise, we lose the changes we manually did when we set up the system view necessary steps in the last video. If you see here, this information we manually input in the last video when we explained about the Sega system view. So if we go directly to the configuration tool, make the necessary changes and save, this information will be lost. So I usually made a backup of those files, okay, in order to recover again the information after changing in the configuration tool and save. So this is a very important step. And this file you find directly in the project workspace core include. So FreeRTOS config. So I'm gonna basically copy this file, and for example I'm gonna save this file here in the system view files folder. So this folder here, it doesn't change when we apply anything, any change under the configuration tool, and this will preserve the file here itself. So every time we save a different configuration in the Cube ID, okay, for the configuration tool, this will generate the files again. And when you generate the files again, we're gonna basically copy this backup file, transfer this backup file to the correct folder, which is here, core include, paste the file here, and that's it. So it's a way to preserve the original content of the FreeRTOS config file. So the first thing here inside the graphical tool, we need to enable the USART we're gonna use in our example. So we're gonna use USART1, okay, and we're gonna basically here enable this as asynchronous, and we're gonna configure the parameters here with this bound rate 150 to 100 bits per second, 8 bits, parity known, and 1 stop bit. So we're gonna use the default here. So after that, we're gonna save all and generate the code. We're gonna explore different possibilities in this lesson. Okay, so this video, it's a long video because we're gonna explore many interesting things here. So it's generating, and soon this finishes, this will change the FreeRTOS config.h. So this is the reason why we told you to make a backup of this file, okay, in order to avoid those changes, because it's natural to use the configuration tool in order to make changes in your project sometimes. So here FreeRTOS config.h, you can see that this basically deletes the functionalities we input from the system view, okay, the necessary one we explained in the last video. So now we're gonna basically do, it's a backup. We're gonna restore the backup. So moving to the original folder here, you can see FreeRTOS config. I'm gonna delete this, and here we're gonna copy FreeRTOS config and we're gonna store in the correct folder here. Next important thing, we need right click under the Project Explorer, refresh. All right, so I'm gonna close this file. I'm gonna refresh again. I'm gonna double click and see if it implements the changes. Yes, as you can see here, Segger System View, FreeRTOS.h, and the necessary include definitions here. That's it. So it's very important to make this backup every time we change the information here in the configuration tool. All right. And now we're gonna start our first example. So we're gonna move here to main.c. And the first thing here is you can see after saving the changes in the configuration tool, this automatically uncomment the default task handle creation here. So as we explained it in the video before, we're gonna comment again because we are not using this task, and we're gonna create our own tasks. Also, we're gonna check some information here under the source tab, how MSP, just to make sure, yes, it's still here because it's under the user code area. So this is what we created in the lesson before, okay, for the sys view start be possible. And let's move here to the main and let's start creating our code. So as you're gonna manipulate data using string, okay, I'm gonna include here some user includes. The first one, we need to include the queue itself. So I'm gonna include queue.h, okay, the header file for queue in FreeRTOS API. So I'm gonna include also standard IO, stdio.h. We're gonna include also string.h, and I'm gonna include standard integer.h. So now we have the necessary includes here for the next steps. Good. Let's move to the user code begin here. Okay. And let's implement, let's create here a variable for the queue itself. Okay, the handle for the queue. So this was from the previous video when we explained this system view. Okay, now we're gonna, in the next line, create here a queue handle object. Queue handle underline t. This I will call xqueue. All right, blue color, so it means it found here the struct definition. That's it. So that's next. We're gonna move to the correct place here, RTOS queues. Look at that. User code begin RTOS queues. So this is the place where we're gonna create our queues. So I'm gonna, for this first example, create a 10 element, 32-bit. I'm gonna choose 32-bit queue. So if xqueue, so the return from the xqueue create function. The first parameter, okay, elements, 10 elements. The second parameter, the size of each element, size of unsigned integer, 32 bits. All right. So if this call here, okay, it's equals to null, it means we have some problem for the queue creation, as I already mentioned and explained before. So what we're gonna do here for debugging proposals? Now we have implemented the USART. We have enabled the USART peripheral. So I'm gonna call the whole UART transmit function. How UART transmit. First thing, UART number 1 is the one we choose from the graphical tool. The second thing here is the data, the message. So I'm gonna basically create a message and transmit a message. So the message I'm gonna transmit here, it's error during queue creation. The size of the message, so it's basically if you cover here the message, so you have here 27 bytes. So this is the size for the message. And a timeout, I'm gonna put here 1000 milliseconds for timeout. This is a whole API, and the whole API is based on the timer 6, as I explained in the beginning of this training section of this training. Okay, the first video. So far so good. Here we create the 10 element queue, 32-bit each element. We check if this is okay. If it's not okay, for debugging purposes, we transmit a message in the serial, and the message is error during queue creation. All right, so we create the queue. That's good. And now we need to create the tasks to manipulate the data entries of this queue and the data output of this queue. Okay, the receiving and send information to the queue. So moving forward here, we have here the creation of the task LED 0, LED 1, as we already explained it in the previous video. Now we're gonna use the debug feature. So I'm gonna basically call how UART transmit UART1. This message here, we're gonna put something like that, error during task LED 0 creation. Okay, the size for that 32 bits, 32 bytes, 32 bytes, 1000 milliseconds. So I'm gonna copy and paste this information here to not lose time under the task LED1, and this is I'm gonna change here to LED1. So far so good. The same structure here, it's to create the tasks to manipulate the queue itself. Okay, I'm gonna copy, I'm gonna paste here. Create task to manipulate, in this case, to send the queue. So X task create, I'm gonna create a name for this task. I'm gonna call vtask send queue. Okay, so it's very important to define this task also. Okay, vtask send and vtask receive queue. So we need basically create the task prototype here. So I'm gonna call void vtask send queue, the same as we did for LED 0 and LED 1. We need to define the prototype. So this is PV parameters, and again void vtask receive queue, void PV parameters. So far so good. Moving forward, so it's here basically vtask send queue. So this gonna create here debugging message for this the task send queue. Config minimal stack size, I'm gonna use this one. I'm gonna use here null, priority 1 and null, as we already explained in the previous videos. Okay, the task creation. So here the message error during task send queue creation, and this is basically 37 bytes. We're gonna copy and paste here. This now is the task receive queue. Task receive queue. Minimal stack size, do, 1, do. That's good. If it's different than true, it returns a message for debugging proposals. Error during task receive queue creation. In this case, is 40 bytes. Good. Done this moment, the task creation itself. Now we need to implement the tasks. And let's move to the user code begin for. This area we are using here to implement our tasks. Okay, this is the task LED 0, LED 1, and now we're gonna create a void vtask send queue, the implementation for the queue is sent. So void pv parameters. So far so good, same structure from the previous one. So variable declaration, we're gonna declare an assigned integer 32-bit variable, call it counter send. We're gonna start with 0 here. So this is basically the implementation of the counter itself. We're gonna create also a char tx text 50 array with 50 values to implement some string. Okay, and now of course important, the infinite loop for the function. It's for. Good. And also important, at the very end, delete this task if breakout the loop. We explained all those things in the previous video. Good. So here inside the infinite loop, the first thing we're gonna check if the queue is full, and we're gonna wait until the queue becomes free. So just important information, be careful. If queue never free, the task will wait forever. So this is the first thing here. We're gonna first work with port max delay. I'm gonna explain this, okay? In this case, if the queue is full, okay, it's not empty, it's full, all positions load with some content, the task will wait forever till the task receive, the queue receive task implementation release some position. So it's important to understand the functionalities of this parameter. Okay, so you're gonna put now port max delay. So the task will wait forever. Will wait till the receive tasks release some position in the queue. Okay, if you want to implement something to overwrite when the queue is full, you need to call xqueue overwrite function. Okay, there is another function that gives you the possibility to overwrite even if the queue is full, and this is called xqueue overwrite. So here, after this short explanation, we're gonna create the xqueue send function, and as parameters for xqueue send function, we have here the handle xqueue, the queue created. Okay, here we're gonna put the counter send variable, okay, to send the current counter value, and as I explained, port max delay. Okay, that's good. So if this is equals pd pass, It means include the value in the queue. Okay, send the value to the queue. So I'm gonna send a message as printf tx text. So you're gonna here now put the message in the string tx text. Okay, queue send and the value itself. This is for debugging proposal at this moment, okay? To tell you that the value was stored inside the queue position, okay? So the value here it's d, okay? A new line, counter send. So we are storing here under this string, under this text, queue send value, and here we're gonna store the current counter value and send this to the tx text variable. After that, okay, I'm gonna explain you during this lesson some important things. It's very important when you are working with some peripheral, okay, it's very important to control, okay, this peripheral. This peripheral will be shared between different tasks in this lesson and also in the next videos. In order to control the access for the peripheral, in this case the peripheral is the USART1, okay, is our serial. It's important to share this peripheral usage between those tasks. At the very end, in the last video, we're gonna present the correct way, let's call it like that, but the way we normally use, using mutex for that. It's kind of semaphore control to access the peripheral, okay, task to task. So to avoid two tasks using the same peripheral at the same time, we're gonna basically use now until the next videos some functions for that, okay? And I'm gonna explain the difference between those functions and even using a graphical tool like the system view in order to understand the behavior of those different functions. It's very important. So first of all, I'm gonna comment here one of those functions that is called task enter critical. We're gonna use this later. For this moment, I'm gonna call vtask suspend all. Calling this function from the FreeRTOS API, we're gonna from this place suspend all different tasks. So we are now in the vtask send queue. So when you call that, if another task is ready, okay, to put in the running state, you will not be ready at this moment. Okay, so this is a way to avoid another task going running state by the scheduler and use, for example, the same peripheral, the serial, the USART peripheral. So in this way we avoid the other tasks to be put in running state. Okay, they are not ready when you call vtask suspend. They are in suspended state, all other tasks. But be careful, this is something that it's managed by the user, so it's not deterministic. So the most common way to avoid that is using mutex, which is basically a deterministic functionality from the FreeRTOS. In the future, we're going to explain the mutex, but now, for this moment, don't worry. We are going to use the vsuspend all, vtask suspend all, in order to suspend the other tasks, because this will suspend the tasks just for a short period of time. And this short period of time, it should guarantee that the task now, the send queue task, will get the peripheral, will get the USART peripheral, will send the message to the USART peripheral, will transmit this to the terminal, okay, and when it finishes, we resume again all other tasks. So all other concurrent tasks can now go into the running state. Okay, so at this moment we are suspending all other tasks and we are gonna call how UART transmit and again UART1. This is TX text. The size is string length, TX text, and timeout here. The first example here, I'm gonna use 1000 millisecond. So this is for the UART transmit. Okay, in the UART transmit, we are transmitting based on the UART1. We are sending the task, and here we're gonna put a maximum delay to transmit all these tests. Okay, 1000 milliseconds, but for sure using 150 kilobits bound rate. Okay, for the UART, this will be transmitted in fewer milliseconds. Okay, not 1000 milliseconds for sure, but it's the way. Just putting comment here to use in the future. Task exit critical, and very important, vtask resume all, vtask resume all, counter send. Okay, so as I already mentioned, vtask suspend all will suspend all other tasks, but you can also use vtask suspend, for example, and instead of using suspend all, you can suspend only one task here. Okay, you can suspend the other task that is using the same peripheral, for example, so you avoid using that to suspend other tasks. You're gonna suspend only the one that is directly concurrent for the peripheral itself. It's one possibility here also. Okay, and for the resume, the same thing. Good. Now we're gonna call the vtask delay, and I'm gonna explain also during the sysview analyzing. I'm gonna use 100 divided by port tick period millisecond. So as we explained before, the vtask delay in the previous video for the LED control with 1000 millisecond delay. Now we're gonna use vtask delay with 100 milliseconds. So this goes basically to another state. Okay, so the send queue now will wait for 100 milliseconds to be executed again. Okay, to be ready to be put in running state. Okay, by the scheduler. That's it. So this is the send queue. Now we need to implement the receive queue. Okay, and we're gonna basically copy and paste and make the necessary changes. All right, vtask receive queue. So vtask receive queue. We have here a counter receive instead of counter send variable. We're gonna use the same tx text because it's local variable. Okay, infinite loop. Here I'm gonna change the comment. I'm gonna put here wait until the queue receive some value. And now instead of queue send, this implements queue receive from the X queue. Okay, this is the address to receive the queue value. E counter receive. I'm gonna use port max delay again. Interesting thing. Okay, as queue receive here is using port max delay, it means if nothing was received in the queue, the task itself will not process anything else in this point until some value arrives, of course, in the queue. You can basically comment the vtask delay. Okay, for example, you can basically comment here the vtask delay because you are now under port max delay. Okay, so because task will follow, in this case, follow the cadence from the queue send task. When you put here port max delay, it means the task will stand still wait something arrives, something rises in the queue. So the task send queue will send the value each 100 millisecond to the queue. So basically, this send queue will control the execution of the receive queue task. So this is why we don't need, in this case, to use the vtask delay, because we are using a port max delay in this place here. Okay, but let's keep the vtask delay enabled here just to see the behavior during the analysis in the system view software. Okay, that's good. So queue, counter receive, port max delay, pd max, pd pass, string send, printf, queue, receive value. Instead of counter send, this is counter receive. So far, so good. vtask suspend all, transmit to useart, vtask resume all. Here, there is no counter send value variable, and that's it. Now it's time to transfer this and to analyze this. Okay, but before moving forward, it's important to tell the difference between vtask suspend all, task enter critical, and so on. Okay, in the future, we're going to explore mutex. Okay, as I already mentioned before. Mutex is a very interesting way. Okay, I prefer mutex, of course. The mutex is a kind of semaphore, but it's ready for peripherals. Okay, and the mutex is used to prevent failures. Basically, when the same peripheral, like UART1, is used by two or more different tasks. So later, at the end of this training, we're gonna explore mutex to implement this. But for this moment, we have two possibilities here. The task enter critical, which is basically critical sections, okay? And this task enter critical, it's also like v port enter critical, okay? And this is the best method to use when the section of code is small. The code protected, like here, how you are transmit is a small code. Well, they protect against other tasks accessing the protected data, and protect also against interrupts accessing the protected data. So it's protect against tasks and interrupts, and it fits normally for a small protected area. Good. And vtask suspend all, what it is. This function creates a critical section also without disabling interrupts. So the vtask suspend all important will not disable interrupts. This only protects against other tasks, okay, accessing the same data, the protected data. And is the best method to use when the section of code protected is longer, okay? It's really fast to enter in this case because it's just suspend all the tasks. You're gonna suspend all other tasks, but can take longer to exit in case of many tasks are moving out from the blocked state. So let's start here with vtask suspend all. So before downloading and start the debugging process, I'm gonna show you now how to change here the frequency of our LEDs, okay, blinking. So if you remember from the first video, we show here the implementation of vtask LED 0 and vtask LED 1 tasks, and here the vtask delay, okay, we choose 1000 millisecond for our blinking task. So I'm gonna just change this to 100 millisecond in order to increase the blinking frequency, okay, in our toggling function of our LEDs for both LEDs, LED 0, LED 1. So I'm gonna debug this, transfer the project, and I'm gonna show you by the camera the increase of this blinking frequency. As you can see here, here's the current 1 second blinking task. We are going to now transfer the change we did for 100 millisecond both tasks. So you got here some error. So you're gonna now check what is going on, correct the error, and that's it. So we probably set up something wrong here. Undefined reference to vtask resume all. And we commit a mistake here. And it's good to understand here to show those kinds of troubles using the console, because you're gonna understand that our tool here, it gives us lots of information when we have some error, when you got some error. In this case, of course, vtask resume all, it's not part of the API, and it's x task resume all instead. So you're gonna put here x task resume all, transfer again, and we're gonna probably set up everything fine now. So far so good, 0 errors. So we're gonna now transfer the changes here, and we're gonna see now the blinking task in a higher frequency. Okay, switch. We also connected here, as we explained in previous videos, the USB serial converter. Okay, the USB serial converter here, it's connected to the USART1 ports, so TX and RX, transmit and receive pins, and also the grounding reference for the serial converter. Okay, the USB stick. So is everything fine now? We're gonna resume, and as you can see now with LEDs, we increase the blinking frequency. Good. Now we're gonna understand now some debugging features, some interesting debugging features. And before going to the debug, I wanna show you now the Termit, the software we're gonna use for USART application. So I'm gonna turn off the camera, and we're gonna move here the Termit. And as you can see, it's already working. Okay, as you can see, the tasks for send and receive, they are currently running as well. At the same time, the LEDs are blinking, as I'm gonna show by the camera now. So you have many different tasks working together and in deterministic way with RTOS. That's fine. So let's go in deeper inside the debugging tools and understand this better. But before, I want to show you here this tool, the Termit. It's a very interesting tool for serial tasks debugging, okay, for serial terminal. And as you can see here, the settings is very important to set up in a proper way. So you're gonna work with 150 kilobits baud rate, 8 data bits, 1 stop bit, no parity, okay, no flow control, and we are using here the con number 3. So just some hints for you to set up properly your debugger, okay, your serial terminal, according to the application requirements. So I'm gonna just make here stop. I'm gonna click here in the connection. So now, as you can see here, it collects all information here. Send value 0, receive value 0, send value 1, receive value 1, send value 2, receive value 2, and so on. So it's very, very nice how it works. And now let's generate the necessary information for the Sega system view. Okay, as we explained in the previous video, telling all information about system view, now we're gonna basically stop here. We're gonna pause our application, and we're gonna move here to the expressions, Sega RTT, AAP1. As you can see here, now we have the buffer address, okay, the same as the previous video. So we're gonna basically now open the debugger console, the memory browser here. We're gonna paste this, enter, And this is the information we need to generate for analyzing with the system view software. So you're gonna click here on export, as we already mentioned, showed before. So 4093 bytes is the size of our buffer, 4093 bytes. And we're gonna save this in the same output folder, but now with a different name, trace2.svdat. Gonna press OK, and that's it. Now let's open the Sega system view and check out the information. All right, so we're gonna under File, Load Data, and you're gonna choose trace2svdat. And that's it. Let's start to understand what's going on now. So, all right, the same information here as we explained it before. Okay, and now we have here two newer tasks: task send queue, task receive queue. Okay, just gonna open here this table in order to explore and show some more interesting information. Task LED1 and task LED2, as you can see, this running 100 milliseconds, it increases the CPU load from 0% to 0.01%. Okay, just some interesting information in comparison to the previous lesson. As you can see here, we have the task receive queue. It takes 2.22% of the CPU, and task send queue 1.97%. Now the idle, it's about 95.77%. So we have an increase in comparison to the previous one. We were not using those send and receive queue tasks. All right, so here gonna close and show here the events table here. And as you can see here, when you click under some event, it brings us directly to this event in the time domain. So task LED 0, as you can see here, it's running for about some microseconds. Okay, 11 microseconds. I'm gonna zoom this just to show it's almost nothing, 0.1%. I explained of the CPU load. Okay, so this is task LED 0, task LED 1. This currently here is when we have the vtask delay functionality, as I already mentioned before. It's very interesting, very nice to understand. So this is the send queue. So the first running of the send queue task. Okay. So this is basically when it's called the queue send, generic send. So we have the queue send here under this position here. So what actually is taking a lot of load in this task? So it takes more than 90% of the task execution. It's basically after the XQ generic send. So we have task run, XQ generic send at the very beginning, and after that we have all this information running. So this is basically the serial sending feature. So when we come back here in the task and we see the send queue, okay, it's called the queue send functionality here. So this is pretty fast in comparison to the USART transmit. So when you send this information using the 150 kilobits per second baud rate, so this vtask suspend all, vtask xtask resume all this thing here, it's taking the time from our task. So it's basically what's going on after we call the xq send. So these instructions are consuming the CPU load after xq send. And When you call the vtask delay, as I already mentioned before, this task moves to another state, so it's now waiting to come back to the ready state when it's over the 100 milliseconds. And in this case, we can see here that this task here, task send queue, okay, this is when the task receive queue start to run, okay. So just before finishing here, we have the task receive queue running, the task receive queue calling the generic receive, and as you can see here, we have the task send queue running again just for fewer milliseconds and call the vtask delay here again. So as you can see here, the receive task, okay, the receive queue interrupts, take its action here after this 1.9 millisecond execution of the send queue, executes, okay, and after some millisecond here, microsecond here, actually, the send queue task come back just to finish it and call the vtask delay till it finishes, and the receive queue task proceed again here by the kernel. And what is actually going on when you see this kind of thing happening? It's good to understand. So we have here the sending task, okay, the queue send task running for about 1.9 millisecond, and for some reason here we have a context switch to the receiving task. The receiving tasks proceed for fewer microseconds and release now again to the send task. And the send task finishes and come back again to the receive task. It's easy to understand when we see the functionalities we are using. So we are using the vtask, as I already mentioned before, vtask suspend all, vtask resume all. In the future, instead of using those functions, we're going to use mutex, okay, in order to maintain here the determinism of our applications. So vtask suspend all suspends the execution of all concurrent tasks. All concurrent tasks. So only task send queue it's running. And it's easy to understand because you are using the time slicing scheme here. And with the time slicing scheme, it's basically what we explained in the first video of this training. And we have here, using a tick of 1 millisecond, each concurrent task with same priority, they will be in a slice time of 1 millisecond. Okay, so the concurrent tasks will be changed from 1 to 1 millisecond of execution. So if we have a task that it takes 90 milliseconds to finish its execution, to process all its content, okay, the CPU load, it's about 9 milliseconds. So this we're gonna split using this time slicing scheme. So we have 1 millisecond executing this task, 1 millisecond execute the other task with same priority. It comes back to the first task, execute again 1 millisecond till we finish the necessary execution. So this is the time slicing scheme. Very important, okay? When we call vtask suspend, it doesn't matter the time slicing scheme because we are suspend all concurrent tasks, even the tasks with same priority. So when you see here in the system view, this task here, the receiving queue with same priority, it's not executing under the time slicing scheme because you can see here that actually the send queue, it takes 1.9 millisecond and our tick it's 1 millisecond. So when we call vtask resume all, okay, and after that we call counter send plus plus, this instruction here. So when you call vtask xtask resume all, we release the other tasks, okay, and those tasks now comes to ready state. And basically what's going on here, the kernel itself will check it out. The previous task takes more than 1 millisecond. So now it's time to change to the other tasks, okay? So it's what's going on, what's happening here. So it takes the change here, okay? The kernel basically made the context switch to the task receive queue, and soon as the task receive queue starts to execute here, it calls the xqueue receive functionality, as we can see here, xqueue receive functionality. And after that, so we have just fewer microseconds here to generate again the change for the previous task, because as you can see, 1 to 1 millisecond, it's the time slicing scheme. So we have 1.9 milliseconds, 1.9 something, plus these 23 microseconds. So it means now we have about 2 milliseconds, and now it's time again to come back to the previous tasks, to the send queue. Look at that, it's very interesting, and the kernel does this automatically for us. So it's very important to understand that when you are using the vtask, the suspend all and xtask resume all, we are breaking this scheme. Okay, it's very important to understand. And here again, it executes the send queue, okay, and after that the send queue sends the task to other state with the vtask delay. So now we're gonna wait for 100 milliseconds to execute again the task send queue. But look at that, we have a bunch of execution to proceed in the receive queue. So the receive queue takes action now and will run for about 2.1 millisecond. And no other tasks it's running during this time, because again we use the vtask suspend all, xtask resume all. So it's very interesting to understand this first example here of the queue video in order to see the difference between here the execution times, the functionalities, and so on. So as you can see here, basically we have about 100 milliseconds from the starting of the task's execution, so about 2 milliseconds for this execution, 2 milliseconds for this execution, 1 millisecond for the other tasks, so about 5 milliseconds. And if we sum this to 95.8, we have here basically 100 milliseconds from the beginning of the execution of those tasks to the end. It's very interesting, this execution here. And this task is powerful, as you can see also. So from 1 to 1 milliseconds, we have here this execution, and we basically record this information. And it's working pretty fine, as you can see here. So far so good. I'm gonna now move to some other examples. Now you're gonna play with some changes here. The first example, now we're gonna basically set up the queue send tasks to perform 5 times faster than the receive queue tasks. So for doing that, we basically change here the vtask delay to 20 milliseconds. So the vtask delay for send queue tasks is 20 milliseconds, and the task delay for receive queue it's 100 milliseconds. So this it's what's going on. I'm gonna now open here the termit. I'm gonna connect. Okay, as you can see, we have values from the previous task, from the previous example. We're gonna now call debug. Okay, this we're gonna transfer the project to the development board. And soon as it finishes, I'm gonna clear the information. Now, good, as you can see here, I'm gonna basically run this task, resume, and I'm gonna pause to get the information. And before getting the information, let's come back here to the termit itself. So as you can see here at the very beginning,
when the things starts here. Q send value 0, receive value 0. But we change now the behavior of our tasks. Now the send queue it's 5 times faster. So as you can see by the debugging proposal serial terminal transmission we set up, as you could remember, we set up in our both tasks a debugging feature for the serial over serial connection. So as you can see in the send queue, we send the information telling the user the current counter send value. And of course, in the receive queue, we get also and retrieve this information, send back to the user. Okay, so as you can see here, the send queue is 5 times faster. So we have here queue send value 1, queue send value 2, queue send value 3, queue send value 4. And just after executing all those queue send, we have a queue receive value 1. So it's what's going on. It takes 5 times the vtask transmission, the task, the queue transmitting task, to perform one execution the queue receive task. Okay, and if you remember, our queue is limited. We can store 10 different values in our queue. So in the next execution, we have here again queue send value 5, queue send value 6, 7, 8, 9. So after that, we have the queue receive value 2. So for 10 executions of queue send, we have only at this moment 1, 2, 3 executions of queue receive. And when the queue send reach the value 12, it means now that overload the 10 different items we can store in the queue itself. Okay, so what's going on in this case? So the queue is completely full. We cannot add anything there using the current function for this project. Okay, the function, it's basically queue send. So the queue is full. So this will wait for port max delay until the queue receive the receive queue retrieves that value and get some space under the queue. Okay, so that's the queue buffer. So this is what's going on. So this is the reason why here when you have value 12 stored in the queue send position, okay, here we call the queue receive 3 times, as you can see. So this is why we reach the value 12 to store in the 10 positions of our queue, okay, the queue buffer. And after that, there is no enough space, okay, empty space. And basically what's going on, the queue send put the task here waiting forever, port max delay. So it's waiting until the queue receive executes, get one of those positions, release one of those buffer positions, and then the queue send can perform again, send another value to the last position. And the same thing now, wait for the queue receive. So at the very beginning, the queue send will work actually from 20 to 20 milliseconds. Its frequency, we decided. But after some time, the buffer is full and the send queue will perform basically following the receive queue performance, the receive queue execution frequency. Okay, so this is what's going on. And now, as you can see, we have queue receive releasing some position of the queue, queue send adding some position in the queue, queue receive releasing again, set again, release again, set again. So this is what's going on, and it goes forever. So let's export here and see this using the system view tool. Same thing, Sagar, AAP1. I'm gonna do this only once more, but in the next we're gonna just show directly on the tool. So memory browser, Okay, same position, go, export, and now the trace number 3, 4094. Okay, and now we're gonna open trace number 3. So far so good, and let's see what's going on now, just to understand what's happening, okay, in a graphical way. And as you can see here, look at that. This is the task receive executing only once. From 20 to 20 milliseconds, the task send queue, it's performing its execution. So 1, 2, 3, 4, 5. So executes again the task receive. The task receive executes again, and 1, 2, 3, 4, 5 executions of task send. Task receive executes again. So now the buffer is almost full. And as you can see, execute 1, 2, 3 times. The buffer is full. When the buffer is full, the task receive can't, the task send can't execute again because the buffer is full. Okay, till we release the buffer, calling, okay, the task receive. So when the task receive executes, so release one position, and the task send can basically add a newer value to the queue. And again, the queue is full. We have all this information here till we execute again the queue receive and release one position and have some more space to add a newer value using queue send. So this is very interesting. As you can see here, the task LED is executing from 100 to 100 millisecond. Task LED 1 and also task LED 0. I'm gonna just zoom here to show some interesting thing. So as you can see here, we have some execution of the task send queue. Look at that. Task send queue is executing this place here. We're gonna zoom in. But look at that. Soon as it executes, it's basically checking the queue. There is no enough space to add newer information in the queue. So goodbye the task and wait for the next opportunity to execute again. And when we release, calling the task receive queue, you have more one enough space, so this task send queue can basically perform add informations there. And it's interesting to check here the task send queue. Look at that. When it's called here from the previous execution with task delay, we have basically here an idle task execute for about 220 milliseconds. Idle tasks executing for about 20 milliseconds. Okay, and it executes again the task send queue. So this 20 milliseconds is basically, as we understand, when you come back here to the task, is basically this task delay. So we have a 20 milliseconds delay. After the 20 milliseconds delay, okay, this task send queue goes again for ready state. Okay, it's now executing, and when it starts to execute, it's very fast. The queue send blocks this task again because there's no enough space, free space in the queue. So this is what's going on. So just to show you here, I'm gonna change now to perform 10 times faster. We're gonna now again transfer this modification and see what's going on. So far so good. Let's clean, right, and play. Gonna stop here. And when we implement this 10 times faster, you can see the buffer is full so fast. So really fast, this buffer is full. And after that, it's synchronized. It starts the execution once queue is received, the next queue is sent. So we're gonna do the same procedure again, and we're gonna open the system view just to show the results. All right, so this is what's going on now. As you can see, it executes 10 times faster. The queue is sent 2, 3, 4, 5, 6, 7, 8, 9, 10. Executes the receive 1, 2. It's full. It's completely full, the buffer. And now, as you can see, it will wait forever. So it executes, look at that. 100 milliseconds, it's the delay for the queue receive. 100 milliseconds. 10 milliseconds is now the delay for the queue is sent. Soon as the queue is full, this it's very interesting. As you can see here, it executes after 20 milliseconds only once. So after 20 milliseconds, and this is what's interesting about those functions. It executes only once. So as I already mentioned before, it executes only once because we have here, coming back again, the task. We have here a vtask delay, 10 milliseconds. And after this vtask delay, of course, the task comes back again here to check it out and to add some information in the queue, but the queue, it's full. There is no empty spaces. So it calls port max delay instead of some delay here. So this is why now our task is basically, it's not executing this anymore, but it's clear that the system here it's very robust because the xQSend just change the tasks, just change from its previous state, from the running state. So now the tasks is basically not executing, not using CPU resource, CPU load, and wait till something happen to release some position in the buffer in this case. So look at that, executes once here, calls the xQSend, and now the task will not execute after 10 milliseconds here. It will execute only when it releases some position in the queue. Look at that, as you can see here. And when the task receive queue executes, release the queue position, release some position in the queue, the task send queue executes immediately to perform, to add newer information in the queue. So it's very interesting. It's fantastic this way how it works. The RTOS, okay, the kernel provide all these functionalities. It's very interesting and very useful to understand this. Now I'm gonna just change this a little bit, okay? I will basically in the send queue task include some new information. I'm gonna put here an else. Sorry, not in this position, but here I'm gonna put here an else. So if the queue is full, this task, of course, as I already mentioned before, it's not executing after we release some position in the queue, but we have a 10 millisecond delay. So I'm gonna increase the CPU processing time by doing that, but for debugging purpose and for the training right now, it's okay. So I'm gonna basically call here the vtask suspend all, and I'm gonna transmit some information, okay, just to show you how UART transmit. Okay, I'm gonna copy just for debugging. Okay, so queue is full. Good. And the size of this text information is 14, and that's it. And X task resume all, of course. So by just doing that, gonna transfer. All right, before transfer this to the microcontroller itself, we need here to change this from port max delay, because when you use port max delay, it doesn't matter if our queue is full. This will not check an else functionality here. This will just stay under this position waiting for the queue be released. So we need here to change here, for example, for 10 divided by port tick period millisecond. So now this goes and check from 10 to 10 milliseconds, and if it doesn't, if it's not equals PD pass, go to the else and will execute and send this message here. Queue is full, as you can see. Good. Now we're gonna transfer and check out this. Resume, connect, and now as you can see, look at that, queue is full, queue is full, queue is full. So it's working. I'm gonna reset the microcontroller, stop, and as you can see, now it's correct. Queue receive 0, queue send 1, 2, 3, 4, 5, 6, 7, 8, 9, queue receive 1, send 10, 11, and executes here. Look at that, queue is full, queue is full, queue is full, queue receive value 2, queue send value 12, queue is full, 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 receive value 3. Okay, it's working. And now I'm gonna show this under the system view again. So far so good. Okay, and zoom out just to show this information here. Look at that. Now as you can see, when the queue is full, okay, this is what we actually have. So it's about 10 milliseconds, and again plus 10 milliseconds to send the information, the TXT information over serial. The same thing, 10 milliseconds, and again 10 milliseconds to send the information over the serial. Okay, and you're gonna ask me why it's not actually just 10 milliseconds between each trial here to send this information to the serial. So it's very interesting question. And when you go here inside, you can see we have two different 10 milliseconds delay. The vtask delay, as I already mentioned before, in this case, when we set up 10 milliseconds delay here in the queue we send, okay, so I don't need here anymore to use the 10 milliseconds delay at this position. So we have two 10 milliseconds delay. The 10 milliseconds for the queue is send function, that's checking out if the queue is free, if we have some position that was released under the queue after 10 milliseconds, and the 10 milliseconds for the task delay at the very end. So this is why we have the difference of 20 milliseconds. So in this case, for example, I can basically comment this task delay because we changed this from the previous value that it was a port max delay. Okay, we changed for a 10 milliseconds delay here, so I don't need to use this vtask delay, and we perform the same thing. So basically, what's going on now? This is the system idle. Okay, so it means it executes, it waits 10 milliseconds after the vtask delay and check by the queue send if some position was released under the queue. So if it was not released, so we set up again a 10 millisecond delay. So this is what actually it's going on here. So it's checking, it's not free, and it takes another 10 milliseconds to check and go check this again. So after that, this moves here, check if the queue it's free. If the queue it's not free, Now it's gonna, because it's just wait this 10 milliseconds and check it again. And if it's not free, this go and execute here the else functionality and transmit this message. Queue is full under the serial port. And we call vtask delay for another 10 milliseconds. So as you can see here, the vtask delay, it's called here, okay, for 10 milliseconds. That's really cool. And we will wait 10 milliseconds again, okay, and we will check if the buffer is empty. If there is some empty space to add, we will execute here basically this functionality. The queue is sent and we will transmit the information and we will add the information under the queue. But if the queue is still full, you will wait again for 10 milliseconds. So that's the magic of these features here. Very interesting to understand the executions here and how to use this such powerful tool. So again, we have 20 milliseconds between each full execution here, okay? It means 10 milliseconds the checking if the queue is full, and 10 milliseconds by the vtask delay of the task, okay? So this is what's going on now. So very, very interesting. All right, now we're gonna change this entirely. Now we're gonna back again here to 100 millisecond delay for the send queue task. Okay, I'm gonna skip this. I'm gonna leave this as was declared before, 10 milliseconds for checking the queue send execution, and instead now we're gonna put the receive queue as fast as possible, 5 times faster in this case. So I'm gonna change completely the behavior of execution. And let's see what's going on. So I'm gonna basically transmit again. Gonna resume. Now as you can see, we have properly running, so it's very fast, okay, and it's synchronized the receive, send information, receive, send information, as you can see here. And let's check it out again in the system view. All right, zoom out here just to show now how it's going on. All right, now you can see the send queue, it's under 100 milliseconds. The send queue is the responsible to add information in the queue. So the receive queue basically follows this behavior, the behavior from the send queue. And the send queue performs from 100 to 100 milliseconds. And as you can see here, 20 milliseconds plus 40 plus 40 milliseconds, okay, just have here about 100 milliseconds from the previous execution to the newer execution. So the send queue adds information in the queue, the receive queue retrieves this information, releases the position in the buffer, and we can perform again after 100 milliseconds. We send a newer value to the buffer and receive the newer value in the buffer. So it's very interesting to check this, okay? You see that the receive task here, this is running just after the send queue is performed. As you can see, this is the send queue. Just after the send queue is performed, the receive queue executes, okay, and retrieve the stored value. And very interesting, the receive queue runs again after 20 milliseconds. Yes, because the vtask delay we set. And if you're gonna open here and check the vtask delay, just move down 20 milliseconds, the vtask delay. But look at that. This task will not run anymore. The receive queue. This will just run again after the send queue is performed. And this is 80 milliseconds later, not 20. Look at that.
It's very important. This is only possible because we set port max delay to the queue receive functionality. As you can see here, port max delay. So this is a very robust and interesting characteristic of the real-time operating system. So the XQ receive function, okay, it's very robust and deterministic. So this means we can save a lot of processing resources using this method. But now let's set some different value, different from port max delay here in the queue receive. So I'm gonna basically again put something like 10 milliseconds delay. So far so good, and transfer this project and check it out. Okay, and now if you see, we have a different behavior. The receive queue, it's performing here, it's executing here 10 milliseconds. Look at that, 20 milliseconds, 10 milliseconds, 20 milliseconds, 10 milliseconds, and so on. So this is actually what is going on. It executes multiple times because we, instead of using here a port max delay, we change to 10 milliseconds, and we still keep here the vtask delay as 20 milliseconds. So this is more or less the same behavior as we check out when you change before in this video the queue is sent. So this is what's going on. So this is why it's important to use the port max delay, because we save some resources when you are doing in this way. Now we're gonna do some changes in our application in order to receive data from the serial port in one task and to send data in another one. So you're gonna do something like an echo functionality. So the first thing here, we need to come back to the graphical tool, and in the graphical tool we're gonna enable the USART global interrupt. So we're gonna start working with ISR in this part of the lesson. So here mode asynchronous disabled, and here we have NVIC settings, and we're gonna basically enable the global interrupt. So at this moment we will keep this priority number 5 for this global interrupt, and that's all. So I'm gonna basically save this and generate the code. And as you can remember from previous lesson, we need to backup. So we need to backup our files. So I'm gonna basically do a backup here for the include folder, and we're gonna basically make the backup of the config.h file as we explained it before. So this is the FreeRTOS config.h, which was modified by the configuration tool right now. So we're gonna delete this, and we're gonna paste the original one after we made the changes for the system view software. So it's very important, as I explained in the beginning of this lesson. And I'm gonna maintain here in the system view files folder the FreeRTOS config.h. So I'm gonna copy this, and we're gonna paste under core include, and that's it. So we're gonna back to Cube IDE, and we're gonna refresh now here under the left tab. So refresh. It seems now FreeRTOS config.h is there with the necessary changes. All right, so this is the first step here in the configuration for the ISR. Okay, good. Second step, after generate the main.c file, this release again the initialization of the default task. We're gonna not use this default task, so we're gonna basically comment the default task. The second thing, and very important to check it out, it's here under the msp.c. The NVIC set priority group is there, so we don't need to call it again. Good. So now let's start to make the necessary configurations for the ISR in the regarding to the USART peripheral. So I'm gonna down here under this MX USART 1 initialization, and here under the user code begin. So here we're gonna call a macro for initialization to enable the interruption under the receive part of the peripheral. So how UART enable interrupt, and as parameters here we're gonna pass the UART itself, which is UART number 1, and the flag for the interruption, and the flag for the interruption will be UART interruption RX, not empty. So when we got something in the receiver part of the peripheral, this will release this interruption, the ISR. So we're gonna enable the interruption based on that flag, interruption reception, not empty. So when you have something in our receiving part. So far so good. This is UART number 1, very important. Good. So the next step now, after configuring that, so we need to create a newer queue, because I want to separate the things here in this lesson. So I'm gonna keep the same queue from the previous explanation, from the previous example, and I'm gonna create a newer one for this ISR UART reception example. So queue handle underline T. This is called XQ UART. So far so good. We need also here, I'm gonna copy and paste to create something for that. So I'm gonna create a task for receiving queue UART, just to tell that. Okay, so receiving queue UART, this is gonna basically the new task we create. So we need here to initialize this task. So I'm gonna copy, paste here. So X task create. So I'm gonna basically create a task for that. This task is receive queue. So I'm gonna basically create a new receive queue UART, the one we just created. Task receive queue UART. And just to change this, I'm gonna change here the priority. I'm gonna elevate the priority for the second one here. Okay, and the message for debugging error during task receive queue, I'm gonna just change a little bit, UART creation, just to separate the things here. So 45 is the size for that. So far so good. Create the task itself. Now we need to initialize also the queue. So I'm gonna create let's see 50 elements. So I'm gonna create a 50 element queue for that. Create a 50 element 8 bits, because it's a ASCII table. So 8-bit queue, it's not enough. So XQ UART, it's equals to XQ create 50 elements, size of unsigned integer 8 equals null. So here the same thing for debugging proposals, and that's it for the moment. Next, we're gonna create in the main.c, in the main.h file, okay, we're gonna here declare something. So here it's the LED 0, LED 1 that was automatically created by the configuration tool. Here under the user area, we're gonna create a function for receiving these values under the serial port. Okay, so the next step we're going to explain about DMA, but right now we're going to use a way to receive this directly from an interruption service routine, ISR. So I'm going to create here a function to receive this data. I'm going to call this like void return function user interrupt, and as parameter for this function we're going to pass the UART underline handle type def, and the type of this is type def, and UART is the name for this parameter. So this is just the input parameter for our UseArt user interruption functionality we are gonna create. Second, we have here the STM32F4XX interruption.c file, and this treats the interruptions we created. So here we have a functionality to handle the UseArt1 global interrupt. So when something happens, when you have an interruption, and our interruption, as you can remember, we configure this interruption based on the receiving, okay, of our UseArt number 1. And if you remember, we configure this, I'm gonna show again, as RX not empty. So when you have something in our reception of the UART number 1, this will automatically release this. I'm gonna save this function here. Okay, UART1 IRQ handler. So at this place here, I'm gonna call this user function we just declare. It's called UseArt user interrupt, and the UART is the UART number 1. It's very, very important. Okay, so this is gonna call the user function, and now we're gonna treat that. We're gonna implement this UseArt user interruption function. Okay, and good. For that, I'm gonna show you now again. Come back to the main.c file, and let's see something interesting here. So I'm gonna down here under the main.c. So the first thing here in the task send queue, okay, I'm gonna keep this as 100 milliseconds, okay, the delay of this task. So just gonna keep it like that. Good. Next, we're gonna to the receive queue here. I'm gonna keep the same thing here. The only thing I'm gonna change here it's this. So we're gonna use this 10 millisecond here timing. Okay, so I'm gonna basically change this right now. Okay, and good, that's fine. I'm gonna keep this as 10 milliseconds, no problem. So this is a way, as I explained it before, I don't need here the task delay at this moment here under the infinite loop of our task, because I already have here implemented inside the queue receive this delay functionality, which is basically 10 milliseconds delay for the receiving queue. Okay, and the receiving queue, of course, it's based on the send queue, on the transmit queue. So the frequency we have here in the transmit queue for adding information in our queue is the frequency that we have here for the receiving queue as well, because this gonna only works, this gonna only go here inside this functionality if we have something new in our queue, some newer information. So that's it. Good. Now we need to create a newer functionality here. So I'm gonna copy this task, a newer task. I'm gonna paste. I'm gonna call this as vtask receive queue UART, the one we declared at the very beginning. We're gonna just keep here is as a assigned integer 8. Gonna use the same, okay, as I declared, and tx text, it's good right now. So the first thing here, wait until the queue receives some value. So xqueue receive, this is the xqueue UART. We're gonna store this in the variable tx text. So first character, only one character at this moment, and I'm gonna use this export max delay. Good. So I'm gonna keep this the same here. I just gonna delete this sprintf. We don't need that. Vtask suspend all. Okay, I'm gonna keep like that. How UART transmit,
this is gonna transmit in the UART1 the TX text, and the TX text here it's a char, and the size it's one, okay, one character, okay, 1 byte in the ASCII table. So this is all here for the moment. So I'm using here port max delay, so I'm gonna use here at the end a delay, a 10 millisecond delay RTOS functionality. Good. So the next implementation is the function we mentioned here, we created here in the main.8 file, the user interrupt, which is basically called inside here when you have the IRQ handler for the USART1. This we're gonna call this. So when we have something new in our USART, okay, some new character in our USART buffer, this is gonna call directly here this functionality. It's called void USART underline user interrupt, and as parameter here we have a UART handle type def, and this is UART. So far so good. Now the implementation. Okay, so the first thing here, the local variable. The first variable here is an assigned integer 8 underline t called rx char, the character we receive under the serial. So this is going to be a static variable, so a static port base type called x higher priority task woken. Very important. So when we're gonna work with ISR interrupt service routines using here RTOS, we're gonna always work with this concept. We're gonna always work with this higher priority task woken flag here, and this is basically a control between the tasks for the operating system which is running and the ISR. So in the ISR, the case of ISR, when you use an interrupt service routine under the deterministic applications of our RTOS, we need to use this task woken here in order to have this deterministic application running as well. Okay, so it's basically that we're gonna declare this, and every time you're gonna use ISR interrupted service routines, you're gonna see this token. We're gonna see this token, this task token here, which is very important under FreeRTOS deterministic applications. And next, X higher priority task token, starting with PD false, this token. So it starts with PD false. At this moment, we're gonna call how UART receive. As you understand from the peripheral, from the microcontroller, there are other ways to work with interruption in this peripheral for receiving information. I'm gonna work in this way. So I'm gonna create a user functionality. I'm gonna put this function inside the interruption here. Okay, so I can remember here. I'm gonna put this here inside, and I'm gonna treat this manually. Okay, to receive data from the serial port using the interrupt concept. Okay, so how you are to receive this, gonna call inside for the how the UART1 and the address for the RX char, and another very important address here, it's another information here, it's 1 byte, and I'm gonna use here 10 milliseconds maximum for implementation, for waiting the character when you call the peripheral. So how UART receive function goes to the peripheral,
peripheral how UART1, UART1, check it out if we have received this information and save this, store this information on the RX char variable. Good. Now we need to transmit this to the queue because we're gonna read the queue with the new character in another task. So we have a task to control that. Okay, so we need in this case to call the function xqueue send, and this send, it's not this one that we implemented here inside some task like that. Okay, we are inside the interrupt service routine. Remember, we are inside the interrupt service routine, and the interrupt service routine, very important. We need this token, the task walker, okay, in order to organize the things here. And we need to use another functionality. It's how QUEUE send from ISR. I'm gonna click here. We have here as first parameter the queue itself, the queue object. The second one, the data we're gonna put inside the queue, RxChar. And the third one, very important, the task walker. So the token here, X higher task walking. So to control the information, to put this in the correct way, in the correct time domain under the ISR. So it's very important. It's a control for our functionalities. Okay. So the next we're gonna insert, very important, just a commenter, insert the token at the end of interrupt service routine. So now port yield from ISR X higher priority task walker. So far so good. So this is basically the way when we're working with interrupt service routines. We need to work with this task walker, okay, concept here, as you can understand, this token here. So this token controls basically the flow to insert the data in the queue and so on. And at the end, we call port yield from ISR here. Good. So that's it. Very important here. We're gonna use task suspend all, task resume all. As I explained it before, task enter critical also do quite same job, but task enter critical normally blocks interruptions. Okay, so we are working this example with an interrupt service routine. So we don't want to block interrupt service routine. We just want to block at this moment the other tasks to avoid then use the same peripheral in order to transmit information. So we're gonna use basically vtask suspend all and xtask resume all, as I explained it before, because this we're gonna block only tasks, not interruptions. That's it. So we're gonna transmit, we're gonna send some information, and we're gonna observe what's going on under the serial port. So run debug. Okay, build finished, and this is gonna now transmit, download the information in the microcontroller. Good. So I just gonna here terminate. I don't wanna use the system view right now, okay, but later we're gonna use. So I'm gonna terminate this, and we're gonna use the termit in order to understand the flow of the things here. So I'm gonna just check first thing if the comport is the correct one, and good. As you can see, the send queue and receive queue tasks are working fine under the 100 milliseconds period. Okay, as you can see here, each 100 millisecond, something it's put inside the queue and something is released and transmit by the serial as well. Now we need to check out here if the task receive queue UART will basically receive the queue and put this information here under the terminal termit 3.1. So I'm gonna basically put something like that. Testing ISR UART RX, and very important, 0x0A. It's a way to transmit here a new line character, okay? Just to transmit a new line in order to create this a way to the information goes to a newer line, okay? It's very tricky. So when you click here under settings, okay, this I already explained in some other courses I have here, X view, okay, so we are gonna basically work this with hexadecimal information. So we're gonna transmit here a hexadecimal character that will basically send a new line character, a new line under the ASCII table, because 0A, that decimal 10 in the hexadecimal table, in the ASCII table, it's the special character to jump a line. So we're gonna basically create a new line. So in order to organize the information here, I'm gonna transmit that. It's possible also at the end of the test, as you can see here, append line feed in order to do quite the same thing. But I'm gonna transmit this like that in the hexadecimal way. And let's see what's going on. I'm gonna basically here press enter, and I'm gonna pause just to show the information. Good, let's see what's going on. Look at that. TE STENG testing ISR UR RX and new line, jump the line. So as you can see, it's fragmented. So you have a part of the text here, part of the text here, part of the text here. Okay, and we're gonna explain this. Okay, we're gonna explain this later on. So as you can see, it's fragmented because we have concurrent tasks here. Those concurrent tasks are using the same processor, okay, the same core. So we don't have here two cores, and those are concurrent tasks, and they are fighting together for space. Okay, so basically what's going on when we are doing this procedure, we have a part here executing the v task receive QUEUES, which is basically getting each character. Remember, we're gonna insert by this function here, character by character, because it's one here. We insert one character here in our queue. This task here will executing from 10 to 10 milliseconds. So the first 10 milliseconds, this basically probably receive information that two characters are inserted under the queue, like you can see here, TE. So when this task goes to the running state, we'll check the queue. Receive something? Yes. The queue received two characters at this moment. So this is gonna basically retrieve the information here and transfer character by character. So as you can see here, 10 milliseconds. So each 10 milliseconds, we are getting the information from the queue and we are transmitting character by character. So this is the reason why we have here 10 milliseconds get one character, T. Another 10 milliseconds later, get another character, E. So first character, T, transmitted. 10 milliseconds later, the other character. But we have concurrent tasks. Remember, we have this receive queue and send queue. So at the same time, the kernel here tells us that the receive queue needs to be running in running state. So this is the reason why we have the information here fragmented. And we're gonna explain, we're gonna change a little bit this program in order to process this faster and more, how can I say, efficiently. So, but before doing that, I just wanna show something. We're gonna basically here comment the initialization for the task send queue and task receive queue in order to understand if this gonna receive the values in a proper way. So I'm gonna basically here mark all the content I wanna comment. So I wanna comment those functionalities here. Right click, we have here source and add block comment. So we are adding a block comment for the initialization, okay, with the task send queue and the task receive queue. So I'm gonna transmit this again to the microcontroller and let's see now if it works. Okay, good. 0 errors, 8 warnings, good. Gonna clear here, connect. So this is from the previous. Now switch and gonna terminate. So as you can see here, we are not receiving information from the previous tasks because we comment those tasks. So I'm gonna basically transmit the message testing ISR and let's see. Good. Testing ISR UART RX. Again, and again. So as you can see, it's working. Now we're gonna change this a little bit, okay? We're gonna now work with another method. What are the problems followed before, as you can remember? Okay, in the pooling mode, the first thing, it's not flexible enough for data that are randomically sent. The pooling mode. The interrupt mode, okay, we just use right now the interrupt mode. This consumes system resources. This really consumes, because what we are doing here, each byte, as you can remember, each byte that arrives cause a data overflow in the programs, can cause a data overflow. I'm not telling that cause, but can cause a data overflow in programs executing multiple tasks with different priorities, for example. Okay, this is one characteristic of the interrupt. And as you can remember here, we are receiving the information, okay, we are processing this information, we are putting this information under the queue, and this is taking process of our microcontroller byte per byte. That's very important. And now we're going to tell something interesting. We're going to use DMA. DMA allows us to receive a large amount of data, but required, of course, a fixed length for each packet. So we're going to combine now in this methodology the interruption with DMA. So I'm going to explain what we're going to do right now. We're going to mix the good things from the interrupt functionalities and the DMA, which is very powerful because we are not consuming system resource while we are receiving a large amount of data that we gonna explain in the next minutes. So now I'm gonna present this methodology. Basically, just an information. We're gonna combine interrupt and DMA in order to create a logic to determine when the serial receiving port is idle. What does it mean idle? No data is sent within a specific time. So the serial port in idle. When the serial port is in idle, and we're gonna call an interrupt to tell us that some data is waiting for retrieval in the memory buffer. So DMA will be used to transfer the data in the background. So basically we're going to combine something interesting from the interrupt service routines, which in this case we're going to wait the serial port be in idle. So it means the serial port is receiving information under the background. This information is managed by the DMA. Okay, so this is not consuming processing time of the microcontroller, but the interrupt it's checking out until no data is sent to the peripheral in a specific time. So what does it mean? It means probably that a large amount of data that was transmitting arrives in the DMA, okay, arrives in the peripheral. The DMA transfer this directly to some memory position, and probably this information is there, and now the serial port it's free, it's idle, And using this combination, this interrupter will tell us that some amount of data arrives in the DMA. Let's get this amount of data and transmit this amount of data and send this amount of data, for example, to another task. So it's a very interesting combination. Okay, in this combination, we have a powerful resource to under the working tasks, the concurrent tasks working, no CPU usage directly used by the DMA. This information is moving to a buffer in the RAM memory. It's storing this information in this RAM buffer, and some flag will tell us that there are no information arriving in the serial port, and probably the information there it's free to analyze. So it's there to retrieve this information. So it's a very interesting combination we're gonna explain right now. So for that we need to go back the graphical tool. Okay, in the graphical tool we come here under System Core and VIC. So you're gonna see here first thing our user global interruption here, it's with 5 the priority, and here it's under code generation. We're gonna see here the user one global interrupt is there. Okay, I'm gonna basically click here to select for initialization sequence ordering, because I'm gonna explain when we were working with DMA we have some very important thing in the initialization of the functionalities. All right, so this is the first thing we're gonna set. Now we need to set the DMA. Okay, so the USART interruption is set under the position number 1 here. Good. So DMA it's very important. Let's show where we can find information for that. So under here USART1 DMA settings. Now we're gonna add, and this DMA is a reception. We can have DMA for transmitting as well, but in this case it's for the reception. This is the data stream we're gonna choose for the DMA from the peripheral to the memory with a low priority. This is very important. We're gonna work with a circular scheme, circular buffer. So this will basically increase the memory. Okay, we don't want to use a FIFO here because we're going to implement our own methodology. Okay, so data width, we're going to work with byte. Okay, the ASCII characters. Okay, but of course, if you're working with Unicode and so on, you can change directly here. We're going to work with ASCII characters. So I'm going to basically set up here's byte in the circular mode. USART1 DMA string, peripheral to memory, and that's it for this configuration here. Okay, it's important. Okay, some circuits, and I'm gonna show here where are the pins for the USART. Good, here. Okay, some circuits may have been configured with an external pull-up. Okay, what we're gonna explain here, we're gonna also communicate in the default mode, but in order to make sure we have a more stable level in this communication, I'm gonna configure those pins as a pull-up input. So I'm gonna set up a pull-up resistor for the pin PA10 and the pin PA9. Okay, where we can find this information. Okay, I'm gonna show right now GPIO settings. GPIO settings here, as you can see here, no pull-up. It's configured for the transmission, but for the reception, I'm gonna use a pull-up resistor in order to implement this. Okay, good. So we have now a pull-up for that. The speed is very high. Okay, that's it. So now we're gonna generate the code. And again, we need to do the backup of the config.h file. So every time, don't worry. So we're gonna basically move to the include folder here. While it's generating, gonna delete. We're gonna move here to system files folder. Gonna copy that, and we're gonna paste again under core, include, and that's it. Good. So the file is generated. Right click, refresh. Let's see if it's okay. Good, it's there, implemented. And again, main.c, we need to basically comment this task creation. Okay, and let's start our implementation. Let's see one thing here. Let's come to the interrupt and see if it remains okay. Our user, it remains there for the interruption. Okay, that's it. Let's check it out, the MSCP, the NVIC set priority, it's there as well. Good. So now let's come back to the main.c file and see what's going on. So the initialization is okay. So we have here Q, we have a standard integer here. That's good. Now we're gonna create some variable here. Okay, I'm gonna create basically here an extruct. This extruct, I'm gonna call this extruct here as a info. And the members for this extruct will be two members. The first one, an assigned integer 8-bit underline t. This we're gonna call like size string. So the first member will tell us the size of our string. And the second one is the array itself, the data we get from the DMA, okay, from the serial port, and the DMA we allocate this in a RAM memory. So this is called data string, and I'm gonna use 255 positions. So very powerful method we're gonna implement right now. All right, so next, and very important, so we have here the queue. We're gonna use another queue for that. So look at that, I'm preserving the previous examples. I'm just maintaining the previous examples. So this training, basically, we're gonna implement step by step, but we're gonna keep the previous example. So at the end of the training, you have here inside your project all the information you need from the different possibilities in FreeRTOS. So queue handle underline t, xqueue, UART, DMA. So another one, and here I'm gonna implement here a global init 8, call it buffer rx with 255 positions. Okay, good. Now we need to create a task for that, and okay, the prototype, it's void the task receive, and the receive keyword UART DMA. So as I explained, you maintain the previous ones during the training. Good, good, good. So next, now we're gonna move here, and as you can see, very important, we have here the GPIO initialization. We have here the DMA initialization, the UseArt initialization in this sequence. Okay, I'm gonna explain this later. So now I'm gonna call here a how UArt receive DMA. So this functionality, we implement the reception for the DMA. This is basically the how UArt 1 uint 8 underline t. So the parameter we're gonna pass is the buffer rx with 255 values possible there. So we're gonna store received data in a buffer array, with this case a limitation of 255 values. Okay, more than enough for many different applications. Good. So this is the way we're gonna start here the DMA to receive the data from the UART and to store this data directly inside the buffer Rx. Good. So now next, we're gonna basically here, it is very interesting, we're gonna comment this fifth element 8-bit queue because we don't need this queue. So I'm gonna save some memory space here. Okay, we don't need this queue in this example, but we need to create a new one. So I'm gonna copy, I'm gonna paste, and I'm gonna create now a 5 element
unsigned integer 32-bit queue. So I'm gonna explain this. Okay, and this queue here it's xq uart DMA xq create 5 different possibilities, and here it's very important size of, and the size of now it's a size of extruct. So extruct, the struct is the one we just created a few minutes ago, a info. Okay, so look at that, we are creating, and this is very interesting, we are creating here a queue to store an extract information. So we have here a data type. We create this data type with 2 different members. The size of the number of characters was received, and the data string with a possibility of maximum possibility of 255 positions. So look at that. This is a very interesting approach, a very interesting way. So inside this information here, we're gonna store the data from the serial port itself. So for example, we're gonna store here a text with 50 characters. And here in this first member, we're gonna start the number of characters that was received. So if we receive 50 characters, we don't need to know that it's 255. We're gonna store 50 characters here, and we're gonna tell by this member that we have already there 50 characters to process. So this is, I think, the best explanation to tell you about that. Good. So QUEUES DMA initialization we created with 5 different possibilities, 5 different positions, okay, contents, and that's it. Good. So now we're gonna create the task itself. And before creating the task itself, I'm gonna comment the other task we were using before for receiving by the UART here, source block comment, and we're gonna copy and paste a new one. This task now is to receive the queue, okay, by the DMA. So we're gonna basically create this task right now, okay, and I'm gonna here uncomment this because I wanna work with this queue communication working parallel to our now new implementation. So I'm gonna remove the block. So I'm gonna use these concurrent tasks here in order to check this interesting behavior. Okay, so QUEUES DMA. This is QUEUES DMA. Good. I'm gonna increment the minimal stack size because remember, we are using now a structure, and this structure have one of its members is quite big. It says 255 unintergate 255 bytes. So in order to have enough space, I'm gonna configure this here multiplied by 2. So in order to increase our stack size and save more information here. Good. And let's check it out. I'm gonna just here move this to use the same priority of the other tasks. So everybody here are running with same priority. Very interesting. Let's see the result at the end. So here it's error during QUEUES DMA creation, for example. So and this is basically 49. Good. So the next step now is to implement this. Okay, but before we're gonna move here to the initialization of the UseArt. Okay, remember from the previous example, we're gonna comment this, but we need another new initialization because remember we are working mixing functionalities of interruption and DMA, but the interruption functionality I need now it's basically look at that how UART enable interruption,
This is gonna be inside the UART1 peripheral, but now the flag is different. The flag is UART IT idle. So this is the tricky I already mentioned. So this basically enable the serial port idle interrupt. So far so good. Now we're gonna implement the queue itself. We're gonna implement the task itself. Gonna move down here. So I'm gonna keep all this information here because we're gonna use a different way now to implement the user interrupt. Okay, but let's see what we need to do here. And now we need to implement. Just before here, I'm gonna copy and I'm gonna paste, and I'm gonna implement now how queue receive UART DMA. Okay, and instead of uint8 here, we have here a struct ainfo, and this is basically a pointer xinfo tx. Okay, so this is the variable we're gonna use. So QUEUE receive UART DMA. Okay, and this is the px info tx. Port max delay, PD pass, task suspend all. How UART transmit? Now it's interesting. We're gonna transmit here. I'm gonna show the px info tx, and the member we're gonna transmit is the data string, and the size we're gonna transmit here, it's another member from this px info. It's the first member, which is basically the size string. So look at that. This is the reason why we are working this methodology. We take the size string from the first parameter of our struct, just to create a struct. This tells us how many bytes, how many characters arrives in the serial port. So for example, 50 characters. So this is basically take the data string, we take the first 50 characters, and we transmit this under the serial transmission port. So very clear, very clever and interesting methodology. So vtask delay 10 milliseconds and so on. Now user interrupt. So when it's idle, remember we created here to call that when it's idle. So when it's idle, this basically, just to explain again, this basically will trigger this function here, IRQ handler, and this we're gonna call USART user interruption, and USART user interruption is here. We need just to change now in order to fit to our application. So in our case now we change a lot this information here. So gonna basically create here, we're gonna maintain this variable because this variable it's okay. We're gonna call this here as data length, just for storing here the old one. I'm gonna copy, I'm gonna paste, and I'm gonna comment this one, lesson UART interrupt Rx. So we're gonna basically comment this just to keep this as historical information if you wanna in the future check it out. So USART user interruption here is, this is the first one, static the task voking here, and now struct ainfo xinfo rx. We're gonna create it again, another one, struct ainfo, and this is a pointer now, pointer to put in our queue px info rx. This gonna point out to the address of the x info rx. So look at that, this pointer, it's initializing pointing to the address of this instruction here, this struct here. Good. And the uint
8 underline T. This is called data length. So far so good. So first thing, X priori task row PD false, and now we're gonna change this dramatically here. Okay, we just keep this yield from ISR, and now we go and follow the implementation. So if useart1 equals how uart1 dot instance. So if how uart1 its instance it's equals useart1, so it means this comes from the useart1, really comes from the useart1. So this is basically checking if IRQ belongs to useart1. Good. So next, it's another if now is the flag, gonna check it out with this macro how uart get what? Get flag. If the flag inside the uart1 it's uart flag idle. So if the flag is the flag idle itself, so if this is different from reset, so we are basically checking if idle flag. So if it's idle flag, so it means the information arrives in the serial port and it's waiting there to be released, okay, and to be stored. So how uart clear what? Idle flag. Inside which uart peripheral? How uart1. So we check if the flag is idle and we clear this flag to be checked again. Okay, so we're gonna basically here clear idle flag. Good. Now we're gonna basically stop the DMA because it means the information was stored and now the hardware it's not receiving for a while, and if the hardware is not receiving, now we're gonna stop the DMA because we want to save the information that was received. So how uart DMA stop for the UART number 1. So we stop the DMA, and now we're gonna check the size of data that was received. So data length, it's equals 255, which is our maximum of the data length, minus this macro here, how DMA get counter. And this is basically the hardware itself, which is HDMA useart1 Rx. So you're gonna basically tell us that 255 is the maximum minus the get counter. Okay, this gives us the data length, the data that was received. Okay, this is very important. And next we're gonna store this inside our xinfo Rx, which is pointed by the px info Rx, okay, directly. So this is the way to manipulate that. So this is the size string equals data length. Good. So we're gonna basically do now a memory copy. We're gonna copy all the content now. Xinfo Rx.data string. So we're gonna copy to the data string of this variable, which is pointed by the pointer here directly. So one content goes directly to the other one. So this is buffer Rx. So this is very important, buffer Rx. Buffer Rx, if you remember in the implementation here of our DMEA, and I'm gonna move here, look at that buffer Rx. This is the global variable buffer Rx, and this variable can receive up to 255 values. So we're gonna basically here copy the buffer Rx with its data length, the data that was really received at this moment with the idle flag. So we're gonna basically now interrupt save FreeRTOS queue. Okay, so it's very important. If interrupt is used to send data, for example,
the UART TX. Okay, that's it. Okay, interrupt save RTOS queue. So this is basically now what we're going to do now. It's a XQ, very important, XQ receive from ISR. So this is a way to interrupt safely the RTOS queue. So this is why it's so important to use this methodology when we are inside interrupt service routine. The task walking itself, as I already mentioned before, and also last but not least, to use the proper functions, okay, like XQ receive in this case from ISR, okay, is used instead. So the interrupt to put the data on the queue needs to be from ISR. So all different functionalities in RTOS that works inside interrupt service routines have this implemented methodology. So XQ send from what? Send from ISR. XQ, the queue itself we are using UART DMA. Now we're gonna point out to the PX info RX, which is basically receiving all the information from the X info RX. So we're gonna do it like that. And last but not least, the X higher priority task focus. Gonna basically now call again the receive DMA. Okay, we're gonna call the receive DMA because we need to start the DMA again for the next data we received. So an integer 8 underline T asterisk buffer reception, and the size is 255. Good. So the port yield, okay, we're not calling in this place. We're gonna call the port yield here after that because we process all the information and we need to call the port yield from this position. All right, let's go to test now the application. So as you can see, both tasks, the task send queue, task receive queue, are working. Each 100 milliseconds send information. Now we're gonna try to send some text here in order to check out if our application, if our DMI mixed with interrupt application, it's working. So gonna transmit this text, gonna transmit again, and again. I'm gonna stop, and as you can see here, it's working really fine. Testing ISR UART RX, testing ISR UART RX, testing ISR UART RX. So this methodology is fantastic. It's great for working with this proposal. So I'm gonna basically now send, just try to make another test. I'm gonna send a bigger one here. So like that. And that's it. So our buffer in this case is 255 characters, so it's more than enough to send here a bigger texts. So last but not least, here we gonna now explain you how can you, for example, initialize some peripheral like an LCD display in a display task, for example. You can basically do the initialization functions before the infinite loop. So this is will running in the first task execution. So when you put some information, execute some instruction before the infinite loop in each task, this will gonna run only once at the beginning of the task, in the task creation. So I'm gonna explain this. This can be very useful if you wanted to, for example, initialize a peripheral like a display. Okay, so I'm gonna basically here in the send queue and receive queue, I'm gonna put some information here at the very beginning. So if you come here at the send queue and the receive queue, you can basically do something like that. vtask suspend all, how you are to transmit. Okay, just for showing you how it works. We're gonna transmit here some message, like for example here the message I'm gonna transmit is start send queue, and of course the size of this message here 18 bits, 18 bytes. So far so good. So start send queue, we need vtask suspend all, xtask resume all. I'm gonna do the same thing for receive queue here. Start receive queue. All right. So I'm gonna send this program to the microcontroller. I'm gonna try again to make another test. Good. As I want to show here, the very beginning, the initialization, I'm gonna basically here run the application. I'm gonna resume, and as you can see, I'm gonna stop. And look at that. This is the very beginning. Start send queue, start receive queue. Okay, queue send value 0, queue receive value 0, queue send value 1, and so on. Okay, so the message was transmitted: start send queue, start receive queue. And as you can see here, just to show, this was done before the for loop. Actually, currently here, before the for loop. And as you can see, this message is 16, only 16 bytes. I transmit 18 bytes here. So this is the reason why, if you check it out here, we have this null information here. Okay, the other 2 bytes are here. So it's important. It's 16 bits, 16 bytes instead of 18 byte. So far so good. Last but not least, I want to present some interesting debugging functions. Okay, so it's possible to work debugging functions in our FreeRTOS in order to understand some task information. Okay, so to check some task information. To work with those functions, we need first of all to configure this facility, this trace facility, call it trace facility, inside the FreeRTOS config.h file. So you're gonna basically here move to the FreeRTOS config.h file. As you can see here, we have different configurations here, different possibilities here. We have here config use trace facility, as you can see, and it's enabled. So this is very important, first of all. Okay, and second, we need to define here another thing, and as you can see here, user code begin, user code end. Here we can add user code, okay, this user code area. And for example, you can also include these parameters here. We implemented, and every time we change in the graphical tool, as you remember, we need to make a backup of this file and copy and paste the backup again to the original folder. Refresh. So if you include this information here inside the user area, you probably don't have this issue, because the configuration tool, when you save, it generates the code but doesn't affect the user area. Okay, so now I'm gonna define here inside this area config use stats formatting with two T's, formatting functions. And this is one. So I'm gonna enable this. Good, now we come back to the main.c. We're gonna create a specific task here to debug the informations. Okay, so I'm gonna call here void vtask debug, and this is void pv parameters. All right, so task debug, and we're gonna here create task. And we're gonna create the task for debugging proposals. Okay, so vtask debug. Okay, vtask debug, and this task here I'm gonna call like task for printing debug info. Config minimal stack size, I'm gonna also increase this value because we are transmitting a bunch of information inside null, and I'm gonna use the same priority here, priority 1. Okay, and the DMA is using here the same thing. We're gonna double the config minimal stack size. Okay, just some information here. Duty task debug creation. Task debug creation, 32 bytes. So far so good. So we initialize here, we create the debug task. Now we're gonna implement down there the debug task. So I'm gonna implement basically here. So I'm gonna copy and paste like the task LED one here. Gonna copy and paste here at the very end. vtask debug, and now here the initialization. So assigned integer 8, local variable tx text with 200 characters, because it's a debugging test with a bunch of information. Okay, good. So we have one important function here, and this function is called vtask list. Okay, vtask list buffer. Okay, good. So vtask list, we're gonna basically check out the necessary information and store this information here. Okay, next, vtask suspend all. Vtask suspend all, same as we was working before. How UART transmit. Okay, how UART transmit, and now we're gonna send the information here. UART1. This is the message we're gonna send. So basically, at the very beginning here, we're gonna jump 2 lines. Okay, I'm gonna skip 2 lines. The size here is 2. Timeout 1000. All right. So this is the first thing. I'm gonna copy and paste, and between those this function, I'm gonna basically here send the tx text. Tx text, and this tx text here is tx text. the length, str length, tx text. So you're gonna basically run the task list, store the information, the debug information in the tx text variable, okay, suspend all the tasks, concurrent tasks, and transmit by over serial the information from the vtask list function. Okay, so here we're gonna add some new information as well. So memory set, I'm gonna basically delete the information inside the tx text variable in order to use this variable again. So I'm gonna clean the information of this variable tx text. So far so good. And next we're gonna transmit, and before transmit I'm gonna sprintf. I'm gonna format the information inside the tx text variable, and I'm gonna insert here another important information, which is the total free heap size. Okay, in this case this is double bytes, and of course we're gonna jump lines here twice. Good. And this is the function to bring back the free heap size, is the export get minimum, export get minimum ever free heap size. It's a complex name, function name, it's a big one actually. So export get minimum ever free heap size. So this is the name of the function. Okay, and of course we need to transmit this information. So how UART transmit UART1, the data is the tx text, the size is str length tx text, and timeout here I'm gonna insert the same 1000 millisecond again. Good. Here we have the x task resume all, and I'm gonna put a vtask delay here of 5 seconds, 5000 milliseconds, because it's important. The debugging task here, the debugging task use a lot of memory resources, a lot of processing as well. So this is, we need to, if you need to use this functionality, use this before release your software, because before release your final product software, because this consumes a lot. This is just for debugging proposals. So as I told you before, I advise you just use this for debugging, and when you need to use this, because this uses a lot of resources. Okay, so this is what's going on here using the vtask list, and it's very processor intensive function. Okay, so be careful. Just for debugging proposals, I recommend that. So I'm gonna transfer and test this. Good. The error here that was returned is because we skip here the comma. So this is the export get minimum free heap size function. Good. All right, so let's transmit this now and test this functionality. Just gonna terminate here. All right, and that's it. Each 5 seconds this debugging task is running. Okay, each 5 seconds the debugging task is running and bring back some information for us, as I'm gonna explain now. The first row here is the task name. Okay, it provides the task name. So the task for printing debugging info is the one we right now, idle task, LED 0, LED 1, send queue, receive queue, receive queue DMA, okay, timer services. So task names. The second, it's the state machine where the task is right now. For example, R, the task is ready, okay. B, the task is blocked, okay. And for example, if you have S here, is the task suspend, okay. If you have D, the task is deleted. So it's very, very interesting here, okay. So it's basically the state of each task. The task for print is the one that is running right now. So this is with X. It's the one that is running because we are printing the debug information in this case. Okay. The third information is the priority, the task priority. Idle is priority 0. Okay. This timer service priority 2. The others here are priority 1. Okay. This is very important. The fourth column is the stack high water mark, which is basically the minimal amount of stack space that has remained for the task since the task was created. So this is basically the minimum amount of stack size remained for the task. Look at that. The task for printing, 88 bytes remaining. The send queue, 8 bytes. But remember, we at the very beginning when we create the task, and this is very important to understand, when we start the task, we define it to use here 2 times get config minimal stack size, okay. And the receive queue, send queue, it's only config minimal stack size. So this is very important, this debug information, because sometimes you can make a decision to increase or not increase the task stack size based on this debug information here. All right, very interesting. Last but not least, here it's a number, a unique number, which is allocated to the task. Okay, it's just a number, a unique number allocated to the task. So you can see different numbers for different tasks. Task LED 0 is the number 1, LED 1 is number 2, and so on. Okay, so number 5. So as you're gonna see here, when you create, the first one is the task LED 0, task LED 1, task send queue. Okay, so this basically follows this sequence and creates a number for each task here. And the tasks created by the kernel, like the idle tasks, it's number 7 here, the time service number 8. So it's very interesting the way it works, this debugging. And last but not least, the total free heap size. This is the heap size. It remains for our application, 10,048 bytes. Okay, before finishing this video, I mentioned before the difference between vtask suspend all and task enter critical. So just to remember, vtask suspend all will not suspend ISRs, okay? Will not suspend ISRs, interrupt service routines like the C-stick. They are not blocked. But when you use task enter critical, those ISRs will be blocked. But before moving, I want to show you something interesting. So since we start this chapter, since we start this lesson, we made some changes in the graphical tool. We saved those changes and we made a backup from the FreeRTOS config.h file, the only one we made a backup. But if you remember from the previous video, we did a lot of changes using the patch file. So in this case here, you can see there is no C-stick and ISR events recording anymore here in System View tool. So as you can see here, no C-stick events recording anymore. But in the previous lesson, the previous video, you see a lot of those events recording. What it means, we are not recording interrupt service routines right now since the beginning of this video, because we just made a backup from the FreeRTOS config.h file. Okay, when we don't record such events like the C-stick that happens each 1 millisecond, we can store much more information here because we are not storing this information that comes each 1 millisecond. So our recording processing, as you can see here from the previous trace number 8, it takes 1.2 seconds, but we normally recording from 200 to 300 milliseconds. This is the reason why we are recording larger files now, because we miss the SysTick and ISR events. But it's important to record ISR events in order to check all the resources you are employing in your application. So now I'm gonna show you the backup files. We're gonna keep those backup files here as downloadable files in our training. We must download these backup files, save these backup files in a proper folder, and use those backup files every time you change something in the configuration tool and save this configuration. So I want to share this file in the training downloadable files, and those files are freertosconfig.h, but here, as you can see, source file, you have a bunch of other files like the task.c. Inside the include folder, we have freertos.h, task.h, and inside portable folder, we have port.c and portmacro.h. We must save these files. We must replace the original files inside our project folder every time we made a change, every time you save some change in the graphical tool. So we must do that. So I'm gonna copy these files here. I'm gonna copy those backup files here, just now the folder source, as you can see, because these I already copied before at the very beginning, and I'm gonna store these under our workspace project. We have a system view files trace folder. We have here freertosconfig.h, and I'm gonna also save these important files here. And we need to change those files. I'm gonna show you right now the information. If you see here, for example, the patch file tells us what needs to be changed. It's not only freertosconfig.h, as you can see here, which includes those files, those information, those lines, as I explained and mentioned in the video before, but there are other files as well. So here you can see there is freertos.h. Look at that, very important. Task.h, and look at this one, port.c. And in the port.c, as you can see here, we are adding trace ISR, trace interrupt service routine enter, trace interrupt service routine exit to scheduler, trace interrupt service routine exit. But if you see, when we change at the very beginning of this video the configuration tool, we also replace this newer information, this added information. As you can see here in the port.c, there is no here trace ISR enter, trace ISR exit to scheduler, and trace ISR exit, as you can see here. So instead of changing this again manually, I saved the backup files, as I mentioned before, and we're gonna replace those files here by the backup files. So this is the simplest way. I'm gonna show you right now. So the first thing here, as you can see, we have here the source folder. The first one here is the task.c. I'm gonna copy this task.c file, and I'm gonna paste this task.c file here. RTOS bases, middlewares, third party, Sega. Okay, as you can see here, third party, FreeRTOS source, and you can see this file here. Okay, I'm gonna basically paste tasks.c, and I'm gonna replace the file here. So I just replace task.c. I need to do this for the other files as well, and I'm gonna just move here quickly, and I'm gonna show you how it works. So source, include, so these two files here are under include folder, RTOS, middlewares, third party, FreeRTOS, source, include, and we replace the two existing files as well. We are moving back here, system view, source, portable. We need now to copy and place those two files and replace the original ones, and they are located right here. Middlewares, third party, FreeRTOS, source, and now we have here portable, GCC, ARM Cortex M4, the one we are using, and we're gonna replace those files. Last but not least, we come back to the Cube IDE, right click, and we're gonna refresh. Okay, I'm gonna close just to show you the port.c. I'm gonna open again, and let's check if the changes were applied in the file. So you're gonna move here. Okay, as you can see, just moving ahead. Look at that. Trace ISR enter, trace ISR exit to scheduler, trace ISR exit. That's it. So it's working fine. Now we're gonna transfer this project and we're gonna record the information and made some tests. Okay, so as you can see here, the main.c, we are using at this moment vtask suspend all. Okay, we're gonna show the results using vtask suspend all and the results using the trace task enter critical as well. So you're gonna connect our termit and we're gonna resume this. It's working, as you can see, and recording all the information. Just stop to show that it's working. And now we're gonna suspend. We're gonna again do the same procedures, 4095 bytes. We're gonna copy the original place here. We're gonna go to the memory browser, paste, enter, and we're gonna export these as trace 9. And that's it, 4095. Good, now we're gonna open the system view. We're gonna open this file and we're gonna check out the information there. Okay, so far so good. The recording is about 266 milliseconds, which means now, look at that. The ISR routines are recording as well. So this is very important. At the very beginning, we didn't make a backup of those files. We just recorded the information in a larger time to show you the possibilities with queues, okay, as we were explaining in this video. But it's important at the very end to show you how powerful it is. We need to save, we need to store more information, and to store this we need to do those steps back again, and we need to restore those backup files from the previous lesson and change the ones, because we, as I explained, we were using the configuration tool, and every time you use the configuration tool and save, this will change the information in some files, okay, and those files we need to replace, we need to restore the information again in order to save this information in this way. So as you can see here, now we have the SysTick, we have the timers, SVC, and so on, and we are recording those information here. So this is why you also reduce our recording duration time. So far so good. So as you can see here, the SysTick is interrupting our task receive queue, task send queue, as you can see here. I'm just gonna make a zoom to show you properly, and look at that, the SysTick, because we need to record this information in order to understand the behavior of our system. So it's important to record those events. But as I mentioned before, now I'm gonna change this a little bit. So I'm gonna basically replace the SysTick. I'm gonna replace the v task suspend all to task enter critical, just to show you the difference between those. I will not suspend in null, I will not suspend here in the initialization, I will not change in the initialization, for example. I'm gonna change this information here in the cycle routine, and as you can see, I'm gonna just make like that. task enter critical instead of v task suspend all, task exit critical instead of x task resume all, for the send queue, for the receive queue, and also for the send queue, the same thing. Task enter critical, I gonna just comment task resume all and suspend all. That's it. Enough for tracing and enough to show you the difference between those two functions. So I'm gonna basically now run, debug, and we will see the results right now in the system view software. So switch here, resume, connect. It's recording the information, okay, and we're gonna suspend, do the same procedure again. Okay, so we're gonna 4095 positions. Good. Memory browser. Enter. This will be the trace number 10. Last but not least, Sega System View, load trace number 10. Okay, just to show you here at the very beginning, the initialization, we are using the vtask suspend all. Okay, so just to show you in the initialization functions, I'm gonna move here ahead, vtask suspend all for send queue and for receive queue. But when this goes cyclically, we are working with task enter critical and exit critical. And let's move a little bit here further. Okay, this is the information we need to show. Good. And look at that. This is very interesting. Now you can see our SysTick interrupt service routine is executing each 1 millisecond. 1 millisecond. But here you can see the task send queue, it's 1.9 millisecond when it's executing cyclically. Okay, when we are executing this information here, the send and the receive queue. As you can see, we are send this text under serial port, but you are using task enter critical instead of vtask suspend all. Look at that, the result. After 1 millisecond, it doesn't interrupt with the SysTick because you blocked the interruptions when we use this function. Okay, so it's very important to understand that, because when we are working with DMA for the reception and we are using interrupt service routines for receiving the information under the serial port, if we use the task enter critical instead of vtask suspend all, we will block this interruption to be executed on that time. Okay, so this is very important, and this is a interesting information to show you the difference using a graphical tool between those two methods. As I said at the very end, we gonna explore the mutex, and the mutex is the best way to explore these possibilities here. Okay, to execute 2 or more tasks using the same peripheral. Okay, so I hope you enjoyed this video. This was a large video, but I think it was a robust explanation for the QE process, and we mixed it with some other information as well. And see you in the next one.